Well, welcome everybody. This will be part one of our chapter 15 in AP Chemistry. We're going to jump ahead to equilibrium so that we don't get stuck in the second semester with all the tough chapters in the second semester. And I think you should be fine. There's one or two items that we haven't learned yet about rate laws and so on. But it makes no difference really to learning the concepts of equilibrium. So we're going to start today with focusing on the concept of what is equilibrium. What is this number called the equilibrium constant, Kc or Keq as I often call it, and how can we use that to determine at what point an equilibrium reaction is at. So with no further ado, let's take a look at how we can tell reactions that are at equilibrium are shifting left or right. As we learned last year, when you have a reaction and its reverse reaction occurring simultaneously and at the reverse to each other and at the same rate, you've established an equilibrium. So as we can point out on this slide here, when N2O4 dominates, you can notice down here that N2O4, dinitrogen tetroxide, can turn into NO2, and just as easily NO2 can turn back into dinitrogen tetroxide. So spontaneously, if you put a container full of N2O4 in front of your eyes, it looks relatively clear. But as time goes by, indicated with this icon in the upper right, now some brown colors of NO2 begin to appear. And if you let time lapse even more, now you'll see that there's a more even distribution of the brown with the clear versions of NO2 and N2O4 respectively. So we're going to be able to tell a lot of these equilibrium situations because we're going to be able to see a change in color. Now what that meant was we started at the beginning with all of the N2O4, and at the beginning there was no brown NO2. So as the system approaches equilibrium, we start eating up the N2O4 and we start building up the amount of NO2. Now really this is a time versus rate, but basically the reaction that produces the colorless N2O4 slows down and the reaction that produces the brown NO2 speeds up, but then they both reach a point where the forward and the reverse rates are occurring at exactly the same rate. And notice that the line goes flat, and at that point in time we have forward rate equal to the reverse rate, and we've achieved dynamic equilibrium. And the reason why I use the word dynamic is that you can't think of these reactions as actually stopping. Left to right, N2O4 turning into brown NO2 is occurring. Right to left, NO2 turning back into N2O4, which is clear, is also occurring. But because they're happening at equal and yet opposite rates, it seems to appear that no further change is taking place. I often use the analogy of a department store with 50 people in it that has a revolving door. If 10 people are exiting at the same time that 10 are entering, the number of people inside hasn't really changed all that much, and so we've reached this equilibrium. The rates are equal. Now the only way you can shift that is by changing temperature, so we're going to be assuming on all these equilibrium problems that the temperature will be staying constant. Now notice this time the graph has changed a little bit. Now we have time going by, and this is still, this is concentration now. And at the beginning all we had was N2O4 and no NO2. And then as time goes by, we build up more and more of the brown NO2, and we start to eat up the N2O4. We reach equilibrium at our established point in time as long as we don't change the conditions, but please notice that the amounts or the concentrations of the reactant and product do not have to equal each other. They just remain constant. We can represent this in an equilibrium equation as you see here. For expediency's sake, I often used a double-headed arrow, but it's really an arrow going left to right and an arrow going right to left, showing that both the forward, and this is by definition what we call forward, left to right, and the reverse reactions are happening simultaneously. Now that's kind of interesting, but chemists always want things to be quantified. So what we're going to now learn is what is the equilibrium constant, how to write an expression for it, and how we can use that to interpret which side of the equilibrium pendulum we've swung to. Right means going forward, favoring more products until a new equilibrium is established, and left means going in reverse, favoring reactants at equilibrium. So let's take a look at how we do that. Now here are some formulas that we haven't seen yet because this chapter assumes that we've done rate laws, but I don't need you to worry about it too much. Our forward reaction of the dinitrogen tetroxide turning into NO2 can be expressed by something called a rate law. We'll learn about those in another chapter. But basically it says that the rate is dependent upon some constant, the little f means forward, times the concentration of N2O4. So we'll learn how to do these rate laws. Here is the reverse reaction showing that it has a rate law of some constant going in the reverse direction times the concentration of nitrogen dioxide squared. And where that comes from, again, we'll show you in just a moment. Okay, so at equilibrium, the rate forward should equal the rate going to the reverse, so you can set those two expressions equal to each other. And then on top of that, you can rearrange the equation to put the two constants together, and you get something that looks like this. And two constants divided by each other is still a constant. So what we've shown is that in this equilibrium reaction, that there's a relationship between the reactants and products that we can write, and we call this the equilibrium expression. We consolidate that forward and reverse constant together, and now we have something called the KEQ, also referred to as the KC. Now let's back up. Brackets mean concentration of. Most of these are happening in solutions, so we're going to use molarity as the unit of concentration. If we're dealing with gases, as you'll see in a moment, we can also use partial pressures. So you can set up an expression that describes mathematically the relationship between product to reactant in an equation that or reaction that has reached dynamic equilibrium. Here is the generalized format. The small letters stand for coefficients, numbers like 2 or 3 that would be balancing the equation. The large letters stand for either reactants like A and B or products like capital C and capital D. It's always backwards in chemistry. So the way we write equilibrium expressions is take the two products and multiply them by each other, their concentrations, in this case measured in molarity, raise each of them to the power that's the same as the coefficient in the expression. Divide that product of the products by the quantity reactant A times reactant B, each of them raised to the power that is their balanced coefficient in the equation. Now that sounds kind of like a lot of gibberish, so let's show you how easy it is. These are sample exercises that you can see embedded in your textbook, and if you look, I believe I have them in the outline, but if I don't, you can also follow along in your textbook. The question wants you to express or write the expression for these three equilibrium situations. Look how simple it is. The first one, it's only one product and one reactant, so take the concentration of oxygen and raise it to the third power. That's because it has a 3 as its coefficient. And take the concentration of ozone and square it. That's because it has a 2 in its equilibrium expression or equilibrium equation. So that's how simple it is. I'm going to show you later it gets even simpler. If they're aqueous solutions or gases, we include them in our equilibrium constant expressions. However, as you'll see later, if they're solids or liquids, we get to ignore them, but more on that later. So you can see that the NaCl squared, its concentration, divided by, and now you have to multiply nitrogen monoxide squared times the concentration of chlorine to get the expression, part of the expression that should be on the denominator. And finally, letter C is showing, this is what we call a complex silver ammonium complex ion. You can even show silver ions and ammonia reacting to make this silver ammonium complex ion, but it's the same thing. there's no coefficient in front, so we don't have any power that we need to raise that to, divided by the product of silver ions times the concentration of ammonia squared. And then you can either write the expression if that's what the problem asks for, or as you'll see in more complicated problems, we'll be putting numbers in where the concentrations are, or maybe we'll be giving you equilibrium constants and asking you to solve for equilibrium concentrations. That part of it's really pretty simple. Now, what are we going to do with this equilibrium constant? Well, we can also use it to express the equilibrium position for reactions that involve all gases. And so if they're all gases on both the left and the right, you can put in the partial pressure of the two products times by each other. So B is the partial pressure. And notice each of them would be raised to their coefficient. That amount is divided by the partial pressures of the two reactants times by each other, again, each raised to the proper coefficient. Now, this is a part you don't need to worry too much about the derivation. Pivnert should be familiar to you. And if you rearrange it to solve for pressure, you get the expression number of moles over volume times the gas constant, that's who the R is, times the temp in Kelvin equals pressure. This is just showing you where this relationship between equilibrium constant, or Kc, and the equilibrium constant when they're pressure and values and they're all gases, you can connect these two mathematically, and we have one or two problems that we can see like that. So if you plug this into the expression for Kp, then you get something that looks like this. And it's kind of a simple little plug and chug, so that you're going to see that a lot in AP Chem. It'd be great if we understand the derivation of all these, but for right now, let's just try to use it in a way that makes you able to express the equilibrium constant when we're using partial pressures relative to the equilibrium constant when we're using molar concentrations. So let's look what the numbers mean. There's the gas constant. We'll be using this in liter atmospheres per mole Kelvin, so that'll be 0.0821. The temperature, as you remember from last year, has to be in Kelvin. And the little triangle means delta. N stands for number of moles. So that's the number of moles change. And it's pretty easy to calculate this. So let's go ahead and take a look at a sample problem. Here is a famous process called the Haber process. They're all gases. So I could write a Kp expression. Or they could give me the Kc, give me a temperature, and ask you to calculate the Kp. So let's take a look at how easy that is. So we have the expression down here. The Kp, what we need to solve for, will be equal to the Kc times the gas constant, that's that 0.0821, they should have put the units in there, times the temperature in Kelvin, so 573 comes from adding 273 to 300 Celsius. And then the reason why we're squaring is because this delta N, or change in number of moles, let's look at what happened. We always go backwards in chemistry. We end up with 2 moles of ammonia, and we started with 4 moles total of nitrogen and hydrogen. So 2 minus 4 is a -2. That's where this little -2 guy comes from. This is what we call a plug and chug. So when you simplify this, it really means that it's going to be 9.60 divided by this quantity, but put it in the denominator. Remember, anything that's got a negative exponent is 1 over that number. And so here is the expression for Kp using the calculation where you can convert from Kc. You don't see that a lot. You could have just as easily written a Kp expression with 2 ammonia squared divided by the product of nitrogen times a hydrogen cubed. But for right now, they were asking specifically for you to use that expression. Okay, now this next set of graphics are showing you that you can reach equilibrium from either direction. Here's what's kind of cool in 2 different trials. We start off with a little bit or no N2O4 in trials 1 and 2. Notice the amounts of NO2 are different in the first 2 trials. But when you end up with calculating the equilibrium amounts or concentrations and punch that into the equilibrium expression, that's why they call it a constant. The number didn't change. Notice 3 and 4 are even more cool. You could start with all N2O4, sorry, no N2O4 and all NO2. And the difference, or vice versa, you could start with all N2O4 and no NO2. It doesn't matter. Look what happened to the equilibrium concentrations. They stayed the same, and you get the same equilibrium constant. So the position of equilibrium, as long as you don't change the temperature, is going to be achieved no matter how much reactant or product that you start with in that container. Notice that we always have to specify the temperature. So here is the data from those two trials being graphed. Here's time going by, and they just showed it as representing the concentration of nitrogen dioxide. Notice that it ends up in the same place. Notice that it doesn't again matter. These graphical representations show us in this trial that we started with all hydrogen and all nitrogen, but no ammonia. Or we start with all hydrogen and nitrogen, sorry, no hydrogen or nitrogen and all ammonia. Doesn't matter. We reach equilibrium at the same point in time where the concentrations are going flat, and notice that they're the same concentrations. And it doesn't change unless you change the temperature. So you have to always assume that you will keep the temperature constant. If that changes, then your equilibrium constant changes, and the equilibrium position, as we call it, also changes. So what is that number that we're going to calculate here? What is it going to mean? We're going to get a number. We're going to start actually punching in some values into these problems. And if your number is really much bigger than 1, it means at equilibrium, if you could stick your head inside the container, you'd see more product swimming around than you would see reactants. And that's what I want you to think of. Even though like the container might look brown, and you're thinking, oh, NO2 dominates, that's that brown gas that you can see like in smoggy days in Los Angeles, there's still a little bit of N2O4 kicking around. It's just masked by the fact that there's more product that's brown colored than there is the clear N2O4. So don't forget, the reactions don't stop. But if you reach equilibrium and you've got a KEQ or KC much greater than 1, it means you have more products present at equilibrium. And the reverse is true. If the KQ or KC is much less than 1, it means that there's more reactants present at equilibrium. So when I say shifts right, favors right, drives right, it means you've done something to the equilibrium to make more product being present. And the reverse would be true. If I say it favors the left side of the equation, it means more reactant is present at equilibrium. But both of them are present at equilibrium, and both forward and reverse reactions do not stop. It's dynamic. So now we're going to look at a little graphical representation, which I like because the colors are fairly illustrative. The first part of the question, notice that all three of these containers are the same, and we're representing products and reactants with different color. You can see in part 1 here, there's way more blue spheres, so products are dominating at equilibrium. Looks like it's 6 blue to 4 reds. Let's jump over to the middle section. Very obvious that reactants are dominating at equilibrium, so this KEQ is probably much less than 1. Now we have to compare picture 1 to picture 3. On picture 3, now the red spheres are the products. There's 8 of those to 2 of the reactant. So I would have to say that the greatest equilibrium constant, the one more greater than 1, is pictured on the far right. What's the question want? It wants you to rank these 3 systems in order of increasing equilibrium constant. And I'll come back to the second question in just a second. So if you take a look at our plan here, we just walked our way through that. The more product that's present at equilibrium relative to reactant, the greater the equilibrium constant should be. So in our solution for part A, the amount of product is being shown here as we just described. So the equilibrium constant that should be the greatest is pictured in picture 3. The one that is the smallest is pictured in picture 2, and picture 1 had the intermediate amount of product, less than the one in picture 3, but more than that in picture 2. So that's a nice graphic. Let's look at it again. Part 2 of the question says, If the volume of the containers is 1 and each sphere represents 1/10 of a mole, calculate the Kc for each system. So for example, remember it's backwards. It's always products divided by reactants. They don't show any coefficients here, so this is dead simple. And since it's in 1 liter, we can actually calculate by counting the number of blue spheres, 6 of them. Each represents 1/10 of a mole. So that means I have a total of 0.6 moles in 1 liter, which is 0.6 molar. So you can do the same for part 2 and part 3. And again, these problems are illustrated in your textbook. So having done those calculations, we have 0.6 moles or molarity of the product that was in picture 1. There were 4 spheres that were reactant, and that would give it a 0.4 molar. So product divided by reactant, we have an equilibrium constant of 1.5. We can duplicate the process for the second picture and for picture number 3 as well. And if you punch in the numbers for picture 3, where there were 8 product spheres to 2 reactant spheres, 0.8 molar divided by 0.2, that's got a KEQ or KC of 4. Remember, when the KEQ or KC is much greater than 1, then products are being favored at equilibrium. And as in picture 2, when it's much less than 1, reactants are favored at equilibrium. Finally, you might see some questions on the AP exam and in some of the worksheets that we do about how you can manipulate equilibrium constants. And I'm going to show you some of the slides which might not mean anything, but we'll actually do a problem then that will show you how you can calculate equilibrium constants if you reverse reactions, if you multiply them, or if you have to sum them. And all I'm going to ask my students to do, and probably you remember this from last year, remember the Hess's law problems? We had to answer when we were going to take 2 or more equations and use them to represent one goal equation, and we might have to flip them and write them backwards or multiply them before we can sum and cancel. It's just like that, except it's not Hess's law. So first off, here is the N2O4 reaction turning into NO2. If I was to flip this equation and write it backwards, to find the equilibrium constant for the second equation, it's simply the inverse of the equilibrium constant in the forward direction. You'll just go 1 over 0.212. So here's a problem, and it's the same one, I think, where we ask you, here we're going left to right, the Kc, or what I often call the KEQ, or sometimes just called K, is 1 times 10 to the negative 30. So if we want to find out what the equilibrium constant is for the reverse, notice this is written backwards, then all I do is I take the inverse of 1 times 10 to the negative 30. And here they are showing the work. So that's a handy thing to know. Another thing that you might have to do is you might have to multiply an expression. We'll get into those problems later, but let's just say we had to take this expression that we see here and times everything by 2. Well, if I doubled everything in this equation, what's interesting is that the equilibrium constant is going to be raised to a power that's equal to what you multiplied by. So the equilibrium constant is going to be squared because I doubled everything. And this is the equilibrium constant for the equation as written. This is the equation with everything doubled. This is the KEQ, or equilibrium constant, squared. And the third part is that you might have to sometimes calculate an equilibrium constant for a goal equation. This is kind of that Hess's law thing I was talking about. And the way you do that is if you have 2 or more steps, then the equilibrium constant for your goal equation will be the product of each of the individual equilibrium constants for each of the individual steps. Let's look at a sample problem for that. So here is our 2 expressions that we're going to try to manipulate to add and cancel to yield this expression here. So the first thing I see is, in the first equation, I have 1 hydrogen fluoride turning into hydrogen and fluoride ions. It's the only source of hydrogen fluoride in the both equations. So for me to end up with 2 hydrogen fluorides when I get all done, I have to take that equation and multiply the whole thing by 2. This might be a good time for me to pick up my pen, and let's go ahead and do that problem. So I'm going to take this equation right here and not times it by 2. Come on, little pen guy, here you go. Like I said, you got to be patient with your teacher. So I'm going to take this whole equation and I'm going to times everything by 2. Okay, and that's where so I'll end up with 2HF, sorry for being so primitive here, yields, and I'm still going to draw my double-headed arrow. Getting a little better at this. 2 hydrogens, and 2 fluorides. I feel like I'm in first grade again. Okay, so also, and I forgot a F right there. There we go. So that means for this expression right here, anytime you double an equation, like you have to because I have to have 2 HFs here, then I'm going to take that equilibrium constant, as you see down here, I'm going to square it. And I could write it up here, but I'm not going to do that right now. Now the second expression, it looks okay. Here's an oxalic acid, and there's one, and the amounts match up. And here's an oxalate ion, and the amounts match up. But you can see that this equation had to be flipped and written backwards. So that means what I have to do to that expression is, yep, you guessed it, I'm going to have to take the inverse. So I'm going to have to take 1 over 3.8 times 10 to the negative 6 to get the equilibrium expression for that one flipped. All right, let's move along and get away from Miss Doherty's primitive handwriting here. So here is the inverse of the expression calculated here, and this one was the square of the equilibrium constant for the first equation. And so what you're supposed to do with these, oh, here's a lovely typo. This one says 2.6, that says 2.5. I didn't do that. But regardless of the numbers being wrong, when you're summing 2 equations and you're going to use the 2 equations together to get the goal equation down here at the bottom, then the rule is you multiply each of the KQs or KCs times by each other. There's the one that was made into a, see if I can keep it straight here, yeah, that's the one that was squared, I think, and that's the one that was from the second expression, that's the one that we took the inverse of. So it's really not that hard to do these kind of problems when you combine them. Just watch out for the math mistakes. And that's a good place to stop. We'll pick up on heterogeneous equilibria on the next part of the PowerPoints for this unit.